staying in the afternoon. This person, Konstantinos Baxevanakis, I'm an assistant professor or lecturer, as we call in the UK. And I'm going to talk about some traditional material, no high-end what is here, no 3D printed metals. It's compacted graphite iron, it's cast iron. Collaborative work, as typical, PhD students get the most of the credit. You might ask what we care in 2022 about cast irons. These materials are being used still today in the automotive industry, in pipelines, in brake discs, in trains, and so on and so forth, because of good thermal and mechanical properties, good thermal conductivity, high damping properties, very good resistance. Price-wise, they're good, I would say. We just have discussed a minute ago, and they're pretty decent in high temperature. Although they have their own problems, that's why I'm here today to discuss. Another motivation slide, a bit of the market growth information, so on. But still, if you see there's a projected growth from 7 to 9.5 millions, that's only the UK. In the US, 1/3 of this corresponds to the European Union, which is particularly drastic. You see here the dip as well due to COVID, and then constant growth the years to come. Now that's all for the business. Back to the material science and the mechanics. Why this material is interesting? So what is interesting is its microstructure. This is a typical micrograph or NCM plot, and what you see here is a combination of ferrite, ferritic matrix primarily, and some graphite. Now, based on the shape of these graphitic inclusions, we can distinguish something that is a circular shape called nodular graphite, and then we have two more shapes, namely this one looking like a worm or like a sausage, vermicular graphite, and then we have flakes, either like pieces of paper, some sort of flake graphite. This is what you find in the compacted graphite iron. If you only have this nice sphere, it's called CGI, spherical graphite iron, or ductile iron. There are plenty of studies on that one. To make it a bit more complicated, if you etch your specimens and do your scans again, you see ferrite, maybe you see pearlite in these forms of fine and coarse pearlite. Damage mechanisms, the difference between the matrix and the particles is essentially the coefficient of thermal expansion. So in high temperature you get debonding, decohesion, interfacial damage, that is the title of my talk, but also you have some cracks inside these laminar structures of graphite. Very recently we published this study, experimental modeling, where we did some cyclic load, only thermal load, no mechanical load we studied. And still you could see some decohesion, hopefully here, some fracture of this graphite after 2 or 3 cycles. I wouldn't dare call this fatigue. One more thing to keep from this slide is these rings around these inclusions. They will come handy in a moment. Another parameter for the modeler now is how do these particles look like. So you see in the top row of the studies, what you saw in the micrograph as a circle is essentially a sphere, but not a proper sphere. But if you look at this vermicular particle, remember I saw this looks like a worm, but essentially this is cloud, this is a coral in the sea, I don't know how to call it. Okay? These are some CT scans that we haven't had. So it's no surprise that you see modeling attempts that they neglect completely these particles. They say it's a void, I'm only dealing with the matrix, or I'm taking perfect circle, or even rigid inclusions, and so on, simplifications. Okay? Now to our research approach, I'm only going to refer to the modeling here, not really the experimental part. So we are approaching this problem in a statistical manner. We have a series of micrographs, and we try to quantify things like area of inclusions, distances, angles, and so on and so forth. And we ended up, agreeing with the literature in this spherical graphite, okay, it's a sphere. But for the vermicular, we have 2 different options. This can be somehow modeled as an ellipsoid, as you have here, or as the geometric object of oblate spheroid. This is the shape of the Earth, essentially. The difference is in the axis. In the ellipsoid, you have A equals to C. In the oblate spheroid, you have A is equal to B. And we're going to talk about cubic matrices. Some characteristics here of this statistical investigation show roughly your graphite particle is around 8 to 10% in this material, and if you calculate the modularity, this varies, the majority of these particles fall within this range. So vermicular to flake. Okay, if you have the statistical data, what you can do is homogenization approaches like the ones I showed earlier. So I'm going to talk about two different models here. The top one, you see 30 by 30 by 30 cube, and then one spheroid of this diameter, 50 microns. And then we have, essentially this is a vermicular one, the ellipsoid I mentioned earlier. This aspect ratio we have varied a lot, the angle we have varied a lot, you can find it along the diagonal, and so on and so forth. The second model has this ring around it, okay? And you see this is the ellipsoid, this is the oblate spheroid, the oblate ellipse that I said earlier. They are somewhat different. So this ring around it is a ferrite or perlite layer. Why is that? Because we saw from the micrograph that this can't really, form, these rings can form around inclusions, and area studies so that they can protect the inclusions from being damaged. Now, when it comes to the constitutive laws, again for the modeling, this is the micrograph I used earlier. This is piece of ferrite, so we have data for that are temperature dependent, so from temperature of here up to 500 degrees. This is the operational range of this material. They try really, the automotive industry try to push this envelope higher, 550, 600, etc. Same for the perlite, temperature dependent data. This you can use as is in a model, or you can use your favorite Johnson Cook or that model. And then we have the graphite. Unfortunately for graphite, we don't have any temperature dependent data. Graphite is mostly elastic, and then with very limited plastic portion, brittle fracture there. And on top of that, you can have some interface simulated by some cohesive elements. Now, another trick on how to find these properties for the cohesive, you can do, remember the discussion in the plenary this morning about down indentation, literature, and so on. So this is a study on its own, I would say. Okay, after having all this, obviously we talk about damage, so we need some damage criterion to break graphite. This is a pretty simplistic, I would say, ductile damage criterion, based primarily on the stress axiality and the plastic strain, rate. This is pretty standard in conventional softwares. And we have assumed linear damage evolution after the onset of damage, because again, there's no experimental evidence for that, how fast it's going, if it's non-linear, if it's linear or not. These are now the boundary conditions and the loading conditions. So the two models I showed earlier, the top one, I will not apply any mechanical load, will only be increased from 0 to 500 degrees, as we have done earlier. And because we talk about homogenization here, periodic boundary conditions, meaning the top and bottom have the same displacement, left and right same thing, front, back, they deform. So essentially you have a unit block representing uniform material. The same happens here, but the model has different loading conditions. So what we have here is first an increase of temperature, right? So from 0 we go to 3, 4, or 500. We heat up essentially the material, and then we load it up to 200 megapascal in tension. Why is that? Because we have relevant experimental studies that we can use to validate our model. Okay? So thermomechanical model in the second case. Let me move then to the results. This is results from the first model, so just heating up the cube. It's no surprise that as we are closer to the circular shape, we have almost no damage. And you see this is very small, but as these particles become more elongated, we see a 20% damage. Mind you that these particles can be with a shape factor of 10 to 1 or even 20 to 1, very elongated. Okay, so this lesson corresponds to the shape factor to the ratio of the minor and major axis. Now, when we did a plot along this line, this is our inclusion. We try to explore the stresses, the plastic stresses across this line, the this is a bit contradictory because you again expect your more elongated one to have higher stresses, but because damage has kicked in now, the load bearing capacity of this material has dropped. So that's why you see the more elongated down there, and then up here they all collapse practically to the same point. A few nice images again from the second model now, and the second again heating up, then applying the side load. Nodular shape in two different cases, ferritic ring or perlitic ring here. The main spot here is just this label that when you have a ferritic ring around it, you have damage at around 80 or 90 megapascals. It's much later when there's a perlitic gradient, and that propagates throughout the different temperatures. So 126, 136, these are pretty close amongst, okay, but still there is some shielding, there is some protection of the perlitic layer there. The same effect you can observe in the vermicular. What is to be noted here is that in this first case you get damage initiation just by thermal load, and this is consistent with our prior studies. So if you heat up something quite elongated and not with perfect axis symmetry as the spherical particle here, you have damage at around 400 something degrees. In the other cases, of course, you don't observe damage, but it's consistent that you get more damage to the perlite, more damage to the ferrite rather than to the perlite. And one more here, the plasticization of the matrix as well. The matrix suffers. So again, higher stresses for the ferrite ring, lower stress for the perlite. If I can summarize everything here in these histograms, so what we see here is a nodular spherical case, and these are axes of temperature. So heating up to 300 gives you this distribution of damage, 400 close by, 500 higher. And if you compare this with the perlite case, you see how this histogram moves towards me, so higher damage in this. Sorry, we compare the peak. I mixed it up. So the peak is around here, the perlite, this moves over to the right. And the same happens in the vermicular. So you see much higher damage here in the ferrite rather than the perlite. So I'm summing everything up just to have time here. The incorporation of the microstructure, we say it's not a straightforward task, so we are keeping ourselves away from directly important these micrographs or these CT scans. I would say this is straightforward, but it doesn't give you much because the next piece of material will be quite different. The morphology of the particles affects both the plastic deformation of the matrix and the damage of the graphite. So the initiation is accelerated as we have higher aspect ratio. Then the matrix material influences the discussion about the rings that perlite has a shielding effect. One more will leave. Combined application, obviously, if you have thermal and mechanical load, it's much worse than just thermal. And finally, something similar can be applied to other metal matrix composites. So a lot of people treat cast iron as an NMC. And with that, I would like to thank you for your attention.
Thank you very much.